Parameter versus statistic. So the first thing we need to know is that hypothesis testing is where we try to use our statistics, our values based on our samples, to make a judgment about a current parameter. Okay, something that they currently believe to be true, something that's meant to be illustrated from a population. For the most part, you're aware of some of these already. So if you look in the box below, down here, you'll see that you have the mean, x bar, and mu. You'll also see the ones typical for variance and standard deviation. We're not going to test variance and standard deviation, but you still need to know which one is a population parameter and which one is a sample statistic. So for the mean, the statistic is x bar, the parameter is mu. This is going to be a new one to you. Proportion is the other one we are going to be testing. Another one to think of for proportion is percentage. So when you can essentially turn something into a percentage, so something like 5 out of 12 is a proportion, and when you actually do 5 out of 12 and get the percentage value, that would be your percentage. So a proportion is going to look like a number out of a number of trials. So the statistic for a proportion is p hat. The parameter is just p. So when you want to indicate it's coming from a statistic, from a sample, you'll use p with a little hat above, and if not, then it would just be p. So what you are attempting to do, hypothesis testing is all about taking evidence and trying to use it, as well as probability, to determine whether what we're stating in our hypothesis is reasonable, whether it might be true or not. So another way that people look at this is called significance testing. So it's where you're trying to determine if your sample that you've gotten from your statistics, your sample statistics, is significantly different enough to say that yes, this is indicating a change. Or is it not statistically different enough that it likely just happened by chance? Even if it's something different from what the norm is, we know it's possible that we could get things on the extreme, something pretty high or pretty low, but it's not considered unusual. So we're trying to make that judgment call, whether it's unusual or whether it's just simply it does in fact indicate a change. So this was the example we discussed. Hypothesis testing, does the new drug lower people's blood pressure? So on first glance, if you ask someone, does this drug lower blood pressure, it appears that it does. And then when you ask again, does the drug lower people's blood pressure, you might say, well, yes, it does. Some people might say, no, it doesn't. But here the line becomes a little more blurred. It's hard to tell whether what we're observing is actually a change due to the drug, or is it a change simply due to random factors and not, in fact, an indication of an effective drug. And that's what we try to use this for, is sure, sometimes it may be more obvious, but in other cases, like this one, it's only possible by statistical testing to tell whether something is indicating a significant change and not just, something that happens to be really small or really large by random chance. So here's that same idea shown a little bit more specifically. Statistical significance. The purpose of a significance test is to determine whether the difference between two or more values is too large to be explained by indeterminate error. So another way to say indeterminate error is again, random chance. So again, this is the idea, is there's two curves on each of these pictures. Is the difference between the two curves, and we can do more than two, but is the difference we're seeing between two values, let's say our two curves here, is it so large, is it too large to be explained by, that could just be happening by accident. We want to know the chances of that. Okay, so for example here, these curves are very, very different, and it's likely that this is not happening by chance. If this is where we think the data should be and this is what we're getting, that's unlikely. So again, if this is where you think you should be in terms of your data and this is what you're getting, it's unlikely that you would say, that's happening by accident. Whereas here, there appears to be no significant difference between the two sets of data. But here it becomes a little less clear. If this is where you're expecting your data to be, for the most part, you're expecting something in the blue area and you're getting something more in the purple, is that difference large enough to say that's indicating a change, or no, that's just happening by chance? What are the odds of those two different scenarios? That's essentially what we're looking for here. Is the odds of this happening at random 30%, because that's pretty high, or is the odds of this difference we're seeing 1%, in which case that's not very high and it's likely more due to an actual change. So that's what we're interested in answering here. All right, this brings us to the 5 steps of hypothesis testing. The good news is, as I explained in class, these are going to be the 5 standard steps we're going to use here in our class, and they work for all types of testing. So even when we do 2-sample and ANOVA and CHI, which will be the types of tests that come a little bit later, these are going to be the same steps you're going to follow for each one. So I highly recommend that you take the extra time to learn more about hypothesis testing now. Spend that extra half hour, an hour, whatever it takes to get the best understanding of how a hypothesis test really works, what all the numbers mean, what all the steps mean. Take that time now while you're doing 1-sample testing, and then I think you're going to find that the stuff that comes after is much, much easier if you have that really good foundational knowledge already there. Because it's going to be the same thing for each type of test. So the more we understand now, the better. And the easier I think you're going to find the rest. So, step 1, we're going to go through each step individually in the next slides. It is going to take a while, but like I said, it's good to get through it now, because once you do and you get a pretty good understanding of each step, you're really not going to find you have to learn a lot more when you do the next types of steps. You just have to be able to tell the difference between the types to use them properly. But they all work the exact same way, which is a really nice thing. So we're going to be doing step 1 first, null and alternative hypothesis. So our null is H0 and our alternative is H1. It is acceptable to use HA. I have seen that before. Obviously for alternative, HA for alternative, which you're welcome to do as well, but I'm going to stick with H0, H0, and H1. Step 2 will be to calculate a test statistic. This is where most of the math is going to happen. This is where you'll use one of your tables. You've learned one so far, Z, the normal table. You're going to learn T, F, and Chi by the time we're done. P-value. P-value is a probability that you'll determine from those tables using your test stat. Step 4 will be to make a decision. Again, the decision rule is always exactly the same. Either we decide to reject or not reject H0. And step 5 will be to make an actual conclusion or decision regarding your test. The main difference between 4 and 5 is step 4 is kind of a statistical language type of decision. You're going to say, something is either statistically significant or it's not. You'll either reject or you won't. But in step 5, this is where I want you to try to really make it clear to someone who doesn't understand anything about statistics. They have, no knowledge of what, a p-value or rejection of H0. They have no knowledge of any of that. You're really trying to just lay it out for them, plain and simple. What was the conclusion? Okay. So that'll be step 5, make a decision and conclusion. Step 1, state the null and alternative hypothesis. The null is going to be H0, H1 is the alternative. Something we want to be aware of is that H0 is always the one that is assumed to be true. So what you're putting in your hypothesis is the statement regarding the information that they believe to be currently true. Something that they've found in the past, something that they're currently assuming. That's what goes into your hypothesis. H0 is always the one, equal to, it's always the one that you assume true. And H1 is, they call the one with burden of proof. It's the one where you have to actually try and show, using your information, whether or not it might be true. So equality is always part of H0, and you're going to see that in all the hypothesis, what's in the H0 is an equal sign. In fact, the only difference you're going to see between the two hypotheses, H0 and H1, is the signs themselves. Other than that, there's going to be no difference. You're going to have the same parameter, the same number. The only thing that's going to change is H0 will have an equal sign, and H1 is going to have one of these three signs. And we'll explain how you know which one as we get further into this. Okay. Left tail, right tail, or 2. So when you do develop the hypothesis, and we will go back to I'll go back to showing you exactly how in just a few moments. But when you design your hypothesis, it's going to look something like these. Here. For a two-tailed test, we say that's the equals versus not equal scenario. And what a hypothesis is going to look like, it's going to look like H0 parameter equals some value. Now obviously we're not going to actually write parameter in some value. We're going to substitute in the appropriate information to make that statement true. This is a very general definition, just to give you an idea of how they're going to look. So we're going to replace parameter with things like mu and p, and some value with the appropriate value for the question. But the idea here to see is look at the difference between these two statements. H0 is equal to, H1 is not equal to when it's a two-tailed test. But other than that, we're going to use the same parameter, same value. We're just going to change the sign. How do you know to use a not equal to sign? Well, the reason it's called two-tail is because if you're trying to look at a mean in the middle here somewhere, so you've got a middle value somewhere right here, a not equal to test says, you know what, if I'm trying to test if the mean is 20, if I believe the mean is 20, if someone comes along and wants to perform a two-tail or not equal to test, what they want to say is, I want to show that the mean is not 20. I don't care where it is. I don't care if it's less than. I don't care if it's greater than. I just want to show that it's not 20. Okay, that it's not in the middle. That's my goal here. So that's what yields a two-tailed test, is when someone wants to know that it's not equal to the current value. You don't care if it's bigger or smaller. You just want to show that the number they're assuming does not seem to be correct. So the other half of that, and you might be able to pretty much figure out what the other two are based on that explanation, but you can also do a left tail test and a right tail test. Okay? And that's along the similar lines, is you have a mean somewhere in the middle. A left tail test says, I want to test that the value that you have assumed, I believe it's less than that number. So that's why it's a left tail, because it's on the left. All numbers that are less than go on the left of the mean. And the right tail test says, you know what, I believe that that number should be higher than what you're claiming. So I'm going to do a greater than that value test, and it's going to be on the right tail, because we know that numbers that are greater than are on the right. When we go through, it's important that you really take your time at that first step. Sometimes we go a little bit too quickly, and that's really the biggest mistake we can make in that first step. The nice thing about hypothesis testing is that the steps are, again, very repetitive. We are doing the same 5 steps over and over again. The biggest disadvantage, the biggest problem I see with hypothesis testing is that students will do the hypothesis part too quickly, or they won't read all the information carefully. And the reason this is such a big problem is that, unfortunately, if you put down the wrong hypothesis in step 1, everything else afterwards is going to be incorrect. There's no other way around it. If you do a two-tailed test and it's supposed to be a left-tailed test, you're going to end up with incorrect information the whole way down. If you choose the wrong test entirely, that's definitely going to yield incorrect results. So it's really, really important that at the very beginning, that's where you should really spend the most time, is choosing the correct test and choosing the correct hypothesis. Don't rush it. You really want to make sure that you get those hypotheses correct. So, on that note, how do you choose left tail, right tail, or 2? Well, at the beginning, it should be relatively clear whether we're trying to determine if we want the value to be bigger than or less than the current value, or whether we're simply just testing against it. When we get a little bit further on into 2 sample testing, it gets a little bit more tricky. There's going to be words used like has improved, is better than, and that's not always going to yield the same sign depending on the variable that's used. So to give you an example, when you're talking about time, the words better or improve actually mean a left tail test. Because you can think about it, if you're running a marathon and you say, did my time improve after so much training, what does that mean for your times? Well, your times would have now been less than before. Whereas on the other side of that coin, if you're talking about, for example, a test score, and you say the words better or improve, what happens if you got a better test score? Well, in that case, the scores have gone up. So you can see that using the exact same words, better, improve, more effective, it could depend on the variable to determine what sign is appropriate. Okay, so we really have to be careful because it could mean less than, it could be greater than. It's all based on context. So really, really take your time and really think about, if this is true, if I do get better, if I do improve, what exactly should happen to my data? Should my data values go up or should my data values go down? Okay, use that as your gauge to tell you whether it's left tail or right tail. It's all about what the data should look like if the reverse is true, if it is in fact true. Alright, so why don't we give it a quick practice as to how we would develop a hypothesis, so what the hypothesis might look like. So the very first thing for now is the only 2 tests we're going to run are proportion or mean, whether we're going to be testing the average or the proportion / percentage. So when it comes to developing your hypothesis, the first thing I would do is I would figure out what type of test am I running, and that depends on a few things. Again, for now, we're just going to have 2 choices, either a test of mean or a test of proportion. Right now, I can say I am testing the mean. I know that because it talks about the mean. Okay, it'll talk about mean, it'll talk about average. Those will be the type of things that I will hear in the question to tell me that it's the mean or the proportion. Now, again, in real life, in real practice, you would know what it is based on your own data. Like, you would know if you're trying to test an average. You would know if you're trying to test, the percent of rats that had a tumor shrink. You would know these things based on your own data and what you're trying to accomplish. So that would be easy enough for you in a real life scenario. It just depends on what you are doing. But in a math class, since we are dealing with a lot of word problems, just to make it clear, you're looking for how the problem is being described. Is it being described in terms of a mean or a proportion? So for now, we're going to use mean. So this is the one that you're most familiar with. So all these ones are going to use mean, but that is the first thing you want to check. Then we want to go about and make our two hypotheses. So H naught should be, if you remember what we showed a few slides ago, H naught should be parameter equals some number. And that's always the one that's assumed to be true. So right now, what are we assuming? We're assuming the mean, mu, monthly pet expenses for household with pets is $71. This is the assumed truth right now. They believe that the average is 71. So they believe that the mean, the mu, oh, that was hard to write on PowerPoint. The mean mu is equal to $71. Right now, that is the assumption. What are you trying to test? That goes in H1. Well, I want to test this statement. So what do they want me to do? They say that this is the mean. I want to test that statement. I want to test that the mean is, well, what's not 71? Well, that would be the alternative. Not 71 would be not equal to 71. So I'm going to test that it's not 71. Okay, I have no reason to test, just less than or greater than. I'm simply trying to test the statement that I've been provided. There's no indication of direction. So I'm going to test that it's not equal to. These are what your hypothesis would end up looking like. H naught, mu equals 71. H naught, I'm testing that mu is not equal to 71. Right, so again, notice the parameters are the same, the numbers are the same. The only thing that changes is the sign. Okay. I would suggest you do a quick pause and try these three if you weren't in class on the Friday. Make sure you know how these three hypotheses came about. Okay. If not, you can keep listening. All right. The average cost of tuition, room and board, is reported to be $8,500 per year. So right now, they believe the average is $8,500 per year. But a financial administrator believes the average cost is higher. So our goal is to test these statements. So right now, the assumption, and the assumption is the H naught, the assumption is that the average, mu, is equal to 8,500. The person believes and wants to test whether or not the average is in fact higher, and higher would be greater than 8,500. There it is there. Number 3, a management wants to know if the mean number, so again there's our average, the average number of dog toys produced is different from 200. So they want to know if it's different from 200. So that would imply that right now they are assuming it is 200. So right now the assumption is that the average is equal to 200. That's the assumption. But what we're trying to test is that it's different from 200. And there's our hypothesis there. All right, finally, management wants to know if the average, they want to know if the average number of cat toys produced has dropped below 200. So again, our assumption is that the average, mu, is equal to 200 currently. But they want to know if it's dropped. So we are going to be testing if it's lower than 200. So this is the assumption, equal, and we're checking to see if it's lower. Okay, that's the idea behind developing a hypothesis. Again, if you look at all the examples, you'll see equals falls into all the H naughts. You'll see the same parameter, same number gets used in both. The only thing you need to do is change the sign of the H1. Okay, after you've chosen the correct test, of course. That's obviously our first step, is to make sure we're actually using the correct hypothesis for the first test, for the correct test. But as long as you've got the right test, then you shouldn't have too many decisions to make about your hypothesis. Just take your time. We'll go through again more about each one so that we don't mix up any numbers. But that's the starting point, okay? right, step 2. Step 2 is where you're going to take your sample information and you're going to use it to calculate a test stat. Now this is very important. You want to use sample information, okay? You don't want to use any of the assumed information. It should be all stuff that has come from a sample that was taken. That's what gets used to make your test statistic, okay? There are many possible test statistics. Every different test has a different test statistic, so that's something you may want to try to keep that information together. Is once you learn a new test, keep the hypothesis and the test stat together with kind of that information as a good little summary to everything that'll be done. Makes everything quick to find and easy to do. For the most part, for the beginning at least, we're going to be using two particular, Z's and T's, and the other ones we're going to be using are called F and chi. Okay, so it looks like an X with a squared. This is called chi-squared. So the very first test statistic you're going to encounter is one that's used for testing the mean when sigma is unknown. Okay, and that's this one here. All right, so this one is for if you've decided to test the mean and sigma is unknown. So you may say, what happens if sigma is known? That's a different test. Just due to time constraints, we don't do it. But essentially, if you're curious, what would happen is the T changes to a Z and the S changes to a sigma. That's what happens if sigma is known. But realistically, it's not very often you would know sigma. Sigma is a population standard deviation. It's not typical that we would know that. It's more likely that you'd be taking information from a sample and figuring out the sample average, sample standard deviation, and sample size. The mu here, and this is important because the other mistake I see, if you haven't made a mistake in hypothesis first step, the next most likely mistake I'd see is right here in this top line of the test stat. Be careful, make sure that you're using X bar, which is your sample mean, minus your population mean. And the population mean is the assumed average. So it's the one that's got to be in the hypothesis. Be careful with the two numbers. You are going to have two averages in a question, in some questions. One of them comes from the sample. One of them is the assumed information, the assumed value, not from a sample. So we want to keep those two straight. The assumed number has to be in the hypothesis and has to go in for mu. The one from the sample has to go in for X bar. So really go slow with those two averages. If you do mix them up, what happens is you get the wrong sign and therefore the wrong p-value and therefore the wrong conclusion. So again, a small mistake will carry on. So do take your time. Make sure you're doing things according to the proper statistics or parameters. Determine the p-value. So determining the p-value is going to happen using two things. Either Excel is going to generate one for us. So we do have some Excel labs.